Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light years across, and stretching for hundreds of millions of light years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions 1 billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival, in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of barophils, pressure-loving organisms, suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environment can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The solar wind that flows through space. From the surface of the sun, an invisible river flows outward in all directions, streaming past the planets and extending far beyond the orbit of Pluto into the distant reaches of the solar system. This is the solar wind, a continuous flow of charged particles, primarily electrons and protons, that escape from the sun's outer atmosphere and race through space at speeds ranging from 250 to over 500 miles per second. This wind carries with it pieces of the sun itself, along with magnetic fields that thread through the solar system, creating an enormous bubble of solar influence that shapes the space environment around every planet. The story of the solar wind begins in the sun's corona, the outermost layer of the solar atmosphere that extends millions of miles above the visible surface. The corona is paradoxically much hotter than the surface below it, while the sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. The corona reaches temperatures exceeding 2 million degrees. This extreme heating, still not completely understood, but likely involving magnetic fields and wave energy, gives particles in the corona so much energy that many of them move faster than the sun's escape velocity. Imagine standing at the sun's surface and throwing a baseball upward. To escape the sun's gravity, you would need to throw it at about 380 miles per second. In the corona, thermal energy heats particles to such extreme temperatures that a significant fraction of them are moving faster than this escape velocity. These particles don't fall back to the sun. They stream away into space, carrying energy and momentum with them. The sun is essentially evaporating, losing mass continuously through this process, though at a rate so slow that it would take trillions of years to evaporate completely. The solar wind is not uniform. It flows faster from some regions of the sun than others, creating a complex structure as it expands outward. Above the sun's equatorial regions, where magnetic field lines tend to loop back to the surface, the solar wind emerges more slowly, typically around 250 miles per second. But at the sun's poles and in coronal holes, regions where magnetic field lines extend far into space, rather than looping back, the wind flows much faster, reaching speeds of 500 miles per second or more. These variations in speed create interaction regions where fast solar wind catches up to slow solar wind. Imagine cars on a highway where fast-moving traffic overtakes slower-moving traffic. The fast solar wind compresses the slow solar wind ahead of it, creating regions of enhanced density and magnetic field strength. These co-rotating interaction regions, named because they rotate with the sun as it spins, sweep through the solar system like a spiral pattern, buffeting planets with alternating streams of slow and fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The magnetic field lines become stretched and twisted, creating a spiral pattern much like water from a rotating garden sprinkler. This interplanetary magnetic field threads through the entire solar system, connecting magnetically active regions on the Sun to the distant reaches of space. When magnetic field lines from different regions of the Sun come together, in space they can reconnect, releasing energy and accelerating particles to even higher speeds. The solar wind is not just a steady breeze but includes violent gusts and storms. When an eruption occurs on the Sun, a solar flare or a coronal mass ejection, enormous quantities of plasma and magnetic field can be hurled into space far faster than the normal solar wind. A coronal mass ejection can contain billions of tons of material moving at speeds up to several thousand miles per second. When one of these structures reaches Earth, typically 1 to 3 days after leaving the Sun, it can compress Earth's magnetic field, trigger spectacular auroras, and potentially disrupt satellites, power grids, and communication systems. The journey of a solar wind particle from the Sun to Earth takes about 4 to 5 days travelling at typical speeds. During this journey, the particle encounters very little. Space between the Sun and Earth is remarkably empty. A cubic inch of the solar wind near Earth contains only about 5 to 10 protons, far more tenuous than even the best vacuum we can create in laboratories on Earth. Yet despite this extreme sparseness, the solar wind carries significant momentum and energy simply because of the vast volume through which it flows and the speeds at which it travels. When the solar wind encounters a planet, what happens depends on whether that planet has a magnetic field. Earth's magnetic field creates a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. The interaction is dynamic and complex. The leading edge of Earth's magnetosphere, called the bow shock, is where the supersonic solar wind first encounters Earth's magnetic field and slows down abruptly, much like air piling up in front of a supersonic aircraft creates a shock wave. This shock heats the solar wind and diverts it around Earth's magnetosphere, creating a turbulent boundary layer called the magnetosheath. Some solar wind particles do manage to penetrate into Earth's magnetosphere, particularly when reconnection occurs between the interplanetary magnetic field and Earth's magnetic field. These particles get funneled along Earth's magnetic field lines toward the polar regions, where they collide with atoms in the upper atmosphere, creating the shimmering curtains of light we call auroras. The green and red colours come from oxygen atoms at different altitudes being excited by these collisions, while nitrogen produces blue and purple hues. Planets without magnetic fields like Mars and Venus experience the solar wind very differently. Without a protective magnetic bubble, the solar wind interacts directly with the upper atmosphere. Over millions of years, this interaction strips away atmospheric particles, carrying them off into space. Mars, which once had a thicker atmosphere and possibly liquid water on its surface, has lost much of its atmosphere to this process. The solar wind literally peels away the outer layers of the Martian atmosphere, particularly during strong solar storms, gradually transforming Mars from a potentially habitable world to the thin, dry atmosphere we observe today. The Moon, with neither atmosphere nor magnetic field, receives the full force of the solar wind directly on its surface. Solar wind particles impact the lunar regolith, becoming implanted in the soil. Over billions of years, this process has altered the chemistry and appearance of the lunar surface, darkening it and creating what scientists call space weathering. Ancient lunar rocks brought back by Apollo astronauts contain trapped solar wind particles that serve as a record of how the Sun's output has changed over time. Giant planets like Jupiter and Saturn have enormous magnetospheres that extend millions of miles into space. Jupiter's magnetosphere is so large that if we could see it from Earth, it would appear several times larger than the full moon in the sky. The solar wind compresses these magnetospheres on the side facing the Sun and stretches them into long tails on the night side. Within these giant magnetospheres, the interaction between the solar wind, the planet's magnetic field, and particles from the planet's moons creates some of the most intense radiation environments in the solar system. The solar wind doesn't flow forever. Far from the sun, billions of miles beyond the orbits of the planets, it begins to slow down as it encounters the interstellar medium, the dilute gas and plasma that fills the space between stars. The Voyager spacecraft, launched in 1977, have travelled far enough to cross the boundary where the solar wind slows to subsonic speeds, called the termination shock. This boundary is not spherical, but is pushed outward in the direction the solar system is moving through the galaxy and compressed in the opposite direction. Beyond the termination shock lies a region called the heliosheath, where the solar wind has slowed but still moves outward, compressed and heated by its interaction with the interstellar medium. The exact shape and extent of this region depend on the strength of the solar wind and the pressure of the interstellar medium outside. Voyager 1 and Voyager 2 have now crossed even farther, passing through the heliopause, the outer boundary where the solar wind effectively stops and interstellar space begins. They are now in a region where the dominant flow is no longer from the sun, but from the galaxy itself. The structure created by the solar wind, this vast bubble of solar influence, extending billions of miles in all directions, is called the heliosphere. It serves as a partial shield, deflecting some of the cosmic rays that stream through the galaxy. Without this protection, the flux of high-energy particles reaching the inner solar system would be higher, potentially affecting planetary atmospheres and creating more radiation hazards for any life on planetary surfaces. The solar wind varies with the sun's activity cycle. During solar maximum, when the sun is most active with many sunspots and frequent eruptions, the solar wind is stronger, more variable, and more likely to include fast-moving coronal mass ejections. During solar minimum, when the sun is quieter, the wind becomes more regular, though still continuous. This 11-year cycle affects space weather throughout the solar system, influencing everything from auroral activity on Earth to the radiation environment encountered by spacecraft. The composition of the solar wind provides a sample of the sun's outer layers. While predominantly hydrogen, both protons and electrons, the wind also contains helium, making up about 4% of the particles, along with trace amounts of heavier elements, like carbon, nitrogen, oxygen, neon, magnesium, silicon, and iron. These heavier elements are present in much smaller quantities but provide valuable information about solar composition and the processes occurring in the corona. Different types of solar wind have different characteristics. The slow solar wind is denser and cooler, while the fast wind is more tenuous but carries more kinetic energy due to its higher speed. Transient events like coronal mass ejections create temporary structures in the solar wind with dramatically enhanced density, speed, and magnetic field strength. These variations create a constantly changing space environment that spacecraft and planets must navigate. The solar wind also carries information outward from the sun. Disturbances created by solar activity propagate through the solar wind, and by observing how these disturbances evolve and interact as they move through space, scientists can learn about the properties of the wind itself and the magnetic fields threading through it. Spacecraft throughout the solar system serve as sentinels, measuring the solar wind's properties at different locations and providing a three-dimensional view of how this invisible river flows through our cosmic neighbourhood. Every star produces a stellar wind, analogous to our solar wind, and these winds play important roles in stellar evolution and in shaping the environments around other planetary systems. Hot, massive stars produce fierce stellar winds that can carry away significant fractions of the star's mass over its lifetime. Cool, evolved stars like red giants produce slower but denser winds. Understanding our own solar wind provides insights into these stellar winds throughout the galaxy, connecting the processes occurring in our immediate space environment to the broader evolution of stars and planetary systems across the universe. the incredible density of neutron stars. Imagine taking the entire mass of our Sun, a sphere so large that over 1 million Earths could fit inside it, and compressing it down to the size of a city. Not a large metropolitan area, sprawling across thousands of square miles, but just the central core, perhaps 12 or 15 miles across. This is a neutron star, an object so dense that a single teaspoonful of its material would weigh about 1 billion tons on Earth. To put that in perspective, that single teaspoon would weigh more than all the cars, trucks and buildings in a major city combined. This density is so extreme that it represents a fundamentally different state of matter, one that can only exist under the most extraordinary conditions in the universe. Neutron stars are born in the violent death throes of massive stars. When a star much larger than our Sun, typically at least 8 times more massive, exhausts the nuclear fuel in its core, it can no longer generate the heat and pressure needed to support itself against its own gravity. The core collapses catastrophically in less than a second, falling inward at speeds approaching 1/4 of the speed of light. The outer layers of the star, rebounding from this collapse, are blown away in a supernova explosion that briefly outshines an entire galaxy. What remains at the center, crushed under its own gravity to densities that boggle the mind, is a neutron star. To understand how neutron stars achieve such incredible density, you need to understand what happens to matter under extreme compression. In normal matter, atoms are mostly empty space. The nucleus of an atom containing protons and neutrons occupies only a tiny fraction of the atom's volume. The rest is empty space with a few electrons orbiting at relatively vast distances. In a solid object, like a piece of iron or a rock, the atoms are packed as closely together as the electromagnetic forces between them allow. But there's still enormous amounts of empty space within each atom. As you compress matter to higher and higher densities, you eventually overcome the forces that keep atoms intact. The electrons are stripped away from their nuclei, creating a plasma of free electrons and atomic nuclei. Compress further, and the electrons themselves are forced to occupy higher and higher energy states due to quantum mechanical principles. Eventually, at densities found in white dwarf stars, electron degeneracy pressure provides the support against gravity. The electrons can't be compressed any further without violating the Pauli exclusion principle, which forbids identical particles from occupying the same quantum state. But if you compress matter beyond even this point, as happens in the core collapse of a massive star, something remarkable occurs. The electrons are forced so close to the protons in atomic nuclei that they combine through a process called electron capture. A proton and an electron merge to form a neutron, releasing a neutrino in the process. This happens not just occasionally, but to nearly every proton in the collapsing core. Within a fraction of a second, the matter that was once composed of atoms, with protons, neutrons and electrons maintaining their separate identities, transforms into a sea of neutrons, packed together so tightly that they're essentially touching. The neutrons themselves now provide the pressure that supports the star against further collapse. Just like electrons, neutrons obey the Pauli exclusion principle and cannot be compressed indefinitely. This neutron degeneracy pressure halts the collapse, but only after the matter has been compressed to densities comparable to that of an atomic nucleus. In fact, you can think of a neutron star as essentially a single gigantic atomic nucleus, several kilometers across, containing more neutrons than there are atoms in all the planets of our solar system combined. The density at the center of a neutron star is estimated to be around 500 million to perhaps 1 billion tons per cubic centimeter. At these densities, a cubic centimeter, about the size of a sugar cube, would contain more mass than Mount Everest. The entire mass of humanity, every person on Earth, could be compressed into a volume smaller than a grain of sand at neutron star densities. These numbers are so far beyond everyday experience that they almost lose meaning, but they represent real physical conditions that exist in these objects. The structure of a neutron star is complex and layered. At the surface, there's a thin atmosphere only a few centimeters thick, composed of hydrogen, helium, or heavier elements, depending on the star's history. Below this lies the outer crust, where matter exists in a crystalline lattice. Here, atomic nuclei, now incredibly neutron-rich and unlike any nuclei found on Earth, are arranged in a solid structure with a sea of electrons moving between them. This crust is extraordinarily rigid. It's been calculated that the material of a neutron star's crust is about 10 billion times stronger than steel. Deeper into the neutron star, at densities about 1,000,000 times that of normal atomic nuclei, the inner crust begins. Here, neutrons start to leak out of the nuclei and form a superfluid that exists between and around the nuclei. A superfluid is a state of matter with zero viscosity. It flows without any resistance whatsoever. This neutron superfluid can exhibit bizarre quantum mechanical behavior on a macroscopic scale. Below the crust lies the outer core, where the density becomes so high that nuclei dissolve entirely into a uniform liquid of neutrons, with a small admixture of protons and electrons to maintain charge neutrality. The neutrons in this region form a superfluid, while the protons form a superconductor, a state where electrical current can flow without resistance. These quantum fluids make up the bulk of the neutron star's interior. At the very center, in the inner core, conditions become so extreme that we're not entirely certain what happens. The density may exceed that of atomic nuclei by a factor of several times. At these densities, neutrons themselves might break down into their constituent quarks, creating what's called a quark-gluon plasma, or strange quark matter. Alternatively, other exotic particles, predicted by physics but never observed, might appear. The center of a neutron star is one of the few places in the universe where matter exists in states that can't be recreated or studied in laboratories on Earth. The incredible density of neutron stars creates gravitational fields so strong that they noticeably warp space-time. At the surface of a neutron star, gravity is about 200 billion times stronger than on Earth. If you could somehow stand on a neutron star's surface, though you would instantly be crushed and vaporized, you would weigh 200 billion times more than you do on Earth. A fall from even a tiny height of 1 centimeter would be fatal, as you would hit the surface at a significant fraction of the speed of light. This intense gravity affects light itself. Photons climbing out of a neutron star's gravitational well lose energy through gravitational redshift. Light that starts as high-energy X-rays at the surface might emerge as lower-energy radiation by the time it escapes into space. The gravity also bends light rays, causing light from the far side of the neutron star to curve around and become visible to an observer. This means you could potentially see more than half of the neutron star's surface at once, as light from behind the star bends around it to reach your eyes. The intense gravity also means that space and time are severely warped near a neutron star. Clocks at the surface of a neutron star run about 30% slower than clocks far away in flat space-time. This time dilation is a real physical effect. Processes genuinely occur more slowly in the strong gravitational field at the surface compared to regions far from the star. The rotation of neutron stars adds another layer of extremes to their already extreme nature. Many neutron stars spin rapidly, some completing hundreds of rotations per second. This happens because of conservation of angular momentum. When the core of the parent star collapses, any rotation it had is amplified enormously as the radius shrinks. Just as a figure skater spins faster when pulling their arms in, a collapsing stellar core spins faster as it shrinks. The result can be a neutron star spinning so fast that its equator is moving at a significant fraction of the speed of light. The fastest spinning neutron star known rotates 716 times per second. Imagine an object with more mass than the Sun, compressed to the size of a city, spinning around more than 700 times every second. The surface at the equator of this neutron star is moving at about 24% of the speed of light. At these rotation rates, centrifugal forces become significant, causing the neutron star to bulge at the equator and flatten at the poles. Yet even with this rapid rotation and the outward force it creates, the neutron star holds together, a testament to the incredible strength of neutron degenerate matter and the overwhelming power of its gravity. The magnetic fields of neutron stars are among the strongest in the universe. The collapse that forms a neutron star compresses and amplifies any magnetic field present in the parent star's core. The result can be magnetic fields 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields even stronger, up to 1,000 times more intense still. At these field strengths, quantum mechanical effects become important. The vacuum of space itself becomes polarized by the magnetic field, affecting how light propagates. Atoms stretched by these fields become elongated, many times longer than they are wide, fundamentally changing their properties. These magnetic fields, combined with rapid rotation, power some of the most energetic phenomena in the universe. Charged particles, accelerated along magnetic field lines, emit beams of radiation from the magnetic poles. If these beams sweep across Earth as the neutron star rotates, we detect regular pulses of radiation, which is why many neutron stars are called pulsars. The precision of these pulses rivals that of atomic clocks, with some pulsars maintaining their timing to within microseconds over years or decades. The density of neutron stars also means that they have very deep gravitational wells. The escape velocity from the surface of a typical neutron star is about 150,000 kilometers per second, roughly half the speed of light. This means that matter falling onto a neutron star from a companion star in a binary system releases tremendous amounts of energy. The infalling material accelerates to these extreme velocities and slams into the surface with incredible force, heating to temperatures of hundreds of millions of degrees and emitting intense X-rays and gamma rays. Neutron stars can also collide with each other in binary systems where two neutron stars spiral together due to the emission of gravitational waves. When they finally merge, the collision creates conditions even more extreme than those in individual neutron stars. The merger produces a burst of gravitational waves that ripple through space-time, along with electromagnetic radiation across the spectrum. These collisions are thought to be the primary source of heavy elements like gold and platinum in the universe, forged in the incredibly dense, hot material ejected during the merger. The study of neutron stars provides a unique laboratory for physics under extreme conditions. The densities, magnetic fields, rotation rates, and gravitational fields found in and around neutron stars simply don't exist anywhere else that we can observe. By studying these objects, physicists can test theories about how matter behaves at nuclear densities, how gravity warps spacetime in strong field regimes, and how quantum mechanics manifests on macroscopic scales. Every observation of a neutron star, every measurement of its mass, radius, rotation, or cooling rate provides constraints on fundamental physics that cannot be obtained any other way, offering glimpses into realms of matter and energy that push the very boundaries of our understanding. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas, and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps space-time, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter, coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms, and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, the simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years. Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the Local Group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. Galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together, shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales, making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope data, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected: rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating 2 searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves, decades before gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The crystal-like structures in space Deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shock waves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. The predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. The thick atmospheres of Jupiter and Saturn. Jupiter and Saturn are fundamentally different from the rocky planets of the inner solar system. They have no solid surface to stand on, no ground beneath the sky. Instead, these gas giants are essentially enormous atmospheres all the way down, layers upon layers of gas that gradually transition from thin upper hazes to dense, crushing depths, where pressure transforms hydrogen into states of matter that don't exist naturally anywhere on Earth. Understanding these thick atmospheres means understanding worlds where the atmosphere isn't just a thin shell surrounding a planet, it is the planet. The atmospheres of Jupiter and Saturn are composed primarily of hydrogen and helium, the two lightest and most abundant elements in the universe. Jupiter's atmosphere is about 90% hydrogen and 10% helium by number of molecules, with trace amounts of methane, ammonia, water vapor, and other compounds making up less than 1%. Saturn has a similar composition, though with slightly less helium, about 96% hydrogen and 3% helium, with the missing helium thought to have settled deeper into the planet's interior over billions of years. This composition mirrors the composition of the Sun and the primordial solar nebula from which the planets formed, marking these giants as worlds that captured and retained their original atmospheres from the planet-forming disk. The visible clouds we see when we look at Jupiter and Saturn exist in the uppermost layers of these atmospheres, in a region where temperatures and pressures allow various compounds to condense into droplets and crystals. On Jupiter, the highest cloud layer consists of ammonia ice crystals forming at temperatures around -150 degrees Celsius, where ammonia gas freezes into white ice. These ammonia clouds give Jupiter's zones, the bright bands that circle the planet, their brilliant white appearance. Below this ammonia layer, at slightly higher temperatures and pressures, ammonium hydrosulfide forms another cloud deck, creating brown and tan colours. Deeper still, water ice and liquid water droplets form clouds, though these are rarely visible from above, hidden beneath the overlying layers. Saturn's cloud structure is similar but more subdued. The planet appears more uniformly golden tan because a high-altitude haze of unknown composition partially obscures the underlying cloud layers. This haze may consist of complex organic molecules called tholins, created when ultraviolet light from the Sun breaks apart methane molecules in the upper atmosphere, allowing the fragments to recombine into larger, more complex hydrocarbons. These organic hazes absorb blue light and scatter red and yellow light, giving Saturn its characteristic buttery colour. The temperatures in these atmospheres change dramatically with depth. At the cloud tops, where pressure is similar to Earth's atmospheric pressure at sea level, temperatures on Jupiter hover around -145 degrees Celsius. On Saturn, they're even colder, around -180 degrees Celsius, because Saturn is nearly twice as far from the Sun and receives less solar heating. But as you descend into these atmospheres, temperatures rise rapidly. The increase comes partly from the Sun's heat that has been absorbed and transported downward, but more significantly from the planet's internal heat. Both Jupiter and Saturn emit more energy than they receive from the Sun. Jupiter radiates about 1.7 times as much energy as it absorbs from sunlight, while Saturn radiates about 1.8 times as much. This extra energy comes from the planet's interiors. Jupiter is still slowly contracting under its own gravity, a process that converts gravitational potential energy into heat through a mechanism called Kelvin-Helmholtz contraction, named after the physicists Lord Kelvin and Hermann von Helmholtz, who described this process in the 19th century. Saturn has an additional heat source. Helium is slowly separating from hydrogen in its interior and sinking toward the center, releasing gravitational energy as it falls. Much like rain falling through Earth's atmosphere releases energy. This internal heat drives powerful convection in the atmospheres. Warm gas rises from the depths, cools as it rises and expands, then sinks back down to be heated again. This convection creates enormous circulation cells that organize the atmospheres into the distinctive banded patterns visible on both planets. Rising gas forms the bright zones, where fresh ammonia ice crystals condense and create white clouds. Sinking gas forms the darker belts, where descending motion prevents cloud formation and allows us to see deeper into the atmosphere, where darker compounds and higher temperatures exist. The winds on Jupiter and Saturn are among the strongest in the solar system. Jupiter's equatorial region rotates faster than the rest of the planet, with winds reaching speeds of about 360 kilometers per hour, roughly 225 miles per hour. Saturn's equatorial winds are even more extreme, racing along at up to 1,800 kilometers per hour, over 1,100 miles per hour, making them the fastest planetary winds in the solar system. These winds are organized into jet streams, narrow bands of fast-flowing gas that separate the zones and belts. The jet streams are remarkably stable, maintaining their positions and speeds for decades or longer. The Great Red Spot on Jupiter is perhaps the most famous atmospheric feature in the solar system. This enormous storm, large enough to swallow 2 or 3 Earths, has been observed continuously since at least 1830, and possibly as far back as the 1660s, when early telescope observers noted a large spot on Jupiter. The storm is an anticyclone, rotating counterclockwise in Jupiter's southern hemisphere, with winds at its edges reaching 400 kilometers per hour. The storm's longevity remains somewhat mysterious. On Earth, hurricanes dissipate within days or weeks when they move over land or cooler water, but the Great Red Spot has persisted for centuries. Its stability likely comes from the fact that Jupiter has no solid surface to create friction and slow the winds, and the storm may draw energy from the smaller storms it absorbs, and from the temperature difference between the warm interior and cold upper atmosphere. Saturn hosts similar, but generally smaller and shorter-lived storms. Approximately once per Saturnian year, about every 30 Earth years, a massive storm erupts in Saturn's northern hemisphere, growing to encircle the entire planet before eventually dissipating. These great white spots, as they're called, were observed in 1876, 1903, 1933, 1960, 1990, and 2010, following a remarkably regular pattern tied to Saturn's seasons. The storms appear to originate when seasonal heating destabilizes the atmosphere, allowing deep, moist convection to punch through the stable layers above and create violent thunderstorms. Lightning occurs on both Jupiter and Saturn, detected by the Voyager, Galileo, and Cassini spacecraft through radio emissions, and in some cases visible flashes. The lightning on these worlds is similar to terrestrial lightning, electrical discharges between regions of different charge within clouds, but can be far more powerful than Earth's lightning. Individual lightning bolts on Saturn have been measured at up to 1 million times more powerful than typical lightning on Earth. These storms occur in the water cloud layer, where the same process that creates thunderstorms on Earth, rising moist air forming clouds and separating electrical charges, operates on these giant planets. As you descend deeper into these atmospheres, the pressure increases relentlessly. At depths of a few hundred kilometers below the cloud tops, pressures reach thousands of times Earth's atmospheric pressure, and temperatures climb to hundreds of degrees Celsius. The atmosphere becomes denser and denser, transitioning gradually from gas to liquid, though there's no sharp boundary, no ocean surface where you suddenly plunge from air into water. Instead, the hydrogen and helium gradually become so compressed that they take on liquid properties, while still being hot enough that calling them liquid doesn't quite capture their state. They exist in a supercritical fluid state, where the distinction between gas and liquid breaks down. Descend even deeper, to depths of 10,000 to 20,000 kilometers, and pressures reach millions of times Earth's atmospheric pressure. Under these extreme conditions, hydrogen transforms into metallic hydrogen, a state of matter where the atoms are squeezed so tightly that their electrons are freed from individual atoms and flow through the material like electrons in a metal. This metallic hydrogen is thought to make up the bulk of Jupiter's mass and a significant portion of Saturn's. It's an excellent electrical conductor, and the flow of metallic hydrogen in these regions, driven by the planet's rotation and internal convection, generates the powerful magnetic fields that both planets possess. The transition from molecular hydrogen to metallic hydrogen isn't abrupt. There's a gradual change over a range of depths where hydrogen takes on increasingly metallic properties. Scientists study this transition using laboratory experiments that compress hydrogen to extreme pressures and sophisticated computer simulations that model how atoms behave under conditions impossible to fully recreate on Earth. Understanding metallic hydrogen is crucial for understanding the interiors of Jupiter and Saturn, yet its properties remain uncertain because the pressures required, several million times atmospheric pressure, can only be achieved briefly in laboratory settings. At the very centers of Jupiter and Saturn may lie rocky cores, though whether these cores exist and how large they might be remains debated. Jupiter might have a core of rock and ice, containing 10 to 20 Earth masses, or it might have no distinct core at all, just a gradual increase in the concentration of heavy elements toward the center. Saturn might have a similar core, though perhaps smaller relative to the planet's total mass. NASA's Juno mission to Jupiter and the Cassini mission's final orbits, diving between Saturn and its rings, have provided gravity measurements precise enough to constrain the planet's interior structures, revealing that both planets have somewhat diffuse cores rather than sharp boundaries between core and envelope. The scale of these atmospheres is almost incomprehensible. On Earth, the atmosphere extends perhaps 100 kilometers before space begins. On Jupiter and Saturn, the atmosphere extends downward for thousands upon thousands of kilometers, transitioning through states from thin gas to dense supercritical fluid to liquid metallic hydrogen. If you could somehow survive the crushing pressures and searing temperatures and descend through Jupiter's atmosphere, it would take days or weeks of continuous falling to reach the planet's center, passing through layer after layer of hydrogen in different states, all of it technically atmosphere, because there's no solid surface to mark where the atmosphere ends. The study of Jupiter's and Saturn's atmospheres extends beyond academic interest. Understanding how these atmospheres work, how convection organizes into bands, how storms form and persist, how energy is transported from the interior to space, helps scientists understand atmospheric dynamics more broadly. The principles governing Jupiter's atmosphere apply, with appropriate modifications, to Saturn's atmosphere, to the atmospheres of Uranus and Neptune, and even to the atmospheres of giant exoplanets orbiting other stars. Some exoplanets, called hot Jupiters, orbit extremely close to their stars and have atmospheres heated to thousands of degrees, creating extreme versions of the processes we observe on Jupiter and Saturn. These thick atmospheres also serve as laboratories for studying hydrogen under extreme conditions. Most of the normal matter in the universe is hydrogen, and understanding how it behaves under high pressure is crucial for understanding not just giant planets, but also brown dwarfs. objects intermediate in mass between planets and stars, and the interiors of low-mass stars. The hydrogen in Jupiter and Saturn exists across a range of pressures and temperatures that spans from Earth-like conditions in the upper atmosphere to conditions approaching those in stellar interiors in the metallic hydrogen regions, providing natural experiments that inform our understanding of matter itself across a vast range of conditions. What comets are really made of? Comets have captivated human imagination for millennia, appearing in the sky as ghostly visitors with long tails that stretch across the heavens. Ancient civilizations often viewed them as omens or messengers from the gods. But these cosmic wanderers are not supernatural phenomena. They're physical objects composed of specific materials that reveal the history of the solar system's formation. Understanding what comets are made of means understanding some of the most pristine, unchanged matter left over from the birth of our planetary system billions of years ago. The core of every comet is its nucleus, a solid chunk of ice and rock that can range from a few hundred meters to tens of kilometers across. In 1950, astronomer Fred Whipple proposed what became known as the dirty snowball model of comets, suggesting that comet nuclei were mixtures of ice and dust. This model has proven remarkably accurate, though modern observations have revealed that comets might be better described as icy dirt balls. They contain more rock and dust than Whipple initially thought, sometimes with dust making up 50% or more of their mass. The ice in a comet is primarily water ice, frozen solid at the incredibly cold temperatures found in the outer solar system. But comets contain more than just frozen water. They also harbour other volatile compounds, substances that evaporate at relatively low temperatures. Carbon monoxide ice exists in comet nuclei, freezing at temperatures even lower than water. Carbon dioxide, frozen into dry ice, is abundant in many comets. Methane, ammonia, formaldehyde, methanol, and hydrogen cyanide have all been detected in comets, creating a chemical inventory that reads like an exotic mixture of the simplest molecules that carbon, nitrogen, and oxygen can form when combined with hydrogen. These volatile compounds exist as ices throughout the comet's interior when it's far from the Sun, creating a porous, fluffy structure rather like hard frozen snow. The density of comet nuclei is remarkably low, typically less than water, around 0.6 grams per cubic centimetre. This low density reveals that comets are not solid blocks of ice, but rather loosely consolidated collections of icy particles with substantial void space between them. Picture a pile of snowballs loosely stuck together rather than a single solid block of ice, and you have a reasonable mental image of a comet's internal structure. Mixed throughout this icy matrix are dust particles, tiny grains of rock and organic material. These dust grains are incredibly small, typically measured in micrometers, smaller than the width of a human hair. They're composed of silicates similar to the minerals found in Earth's rocks, compounds of silicon and oxygen mixed with elements like magnesium and iron. Some grains are pure carbon, forming soot-like particles. Others are complex mixtures of organic molecules, carbon-based compounds that include some of the building blocks of life. The organic material in comets is particularly fascinating. When spacecraft have analysed comets up close, or when laboratories have examined samples collected from comet tails, they've found complex organic molecules, including amino acids, the building blocks of proteins, and nucleobases, components of DNA and RNA. These molecules don't indicate that comets harbour life, but they demonstrate that the chemical precursors necessary for life can form naturally in space and were present in the early solar system. Some scientists have proposed that comets bombarding the early Earth might have delivered substantial quantities of organic molecules and water, potentially contributing to the origins of life on our planet. The European Space Agency's Rosetta mission, which orbited and studied comet 67P/Churyumov-Gerasimenko from 2014 to 2016 provided unprecedented detail about comet composition. The Philae lander, which touched down on the comet's surface, detected 16 organic compounds as the comet's warmth released them from the ice. Among these were 4 compounds never before detected on a comet, including molecules that can act as precursors to amino acids. The comet's surface appeared darker than coal, with a reflectivity of only about 6%, due to the dark organic compounds mixed with the ice. When a comet approaches the Sun, solar heating begins to affect its structure. At distances beyond about 5 astronomical units, 5 times the Earth-Sun distance, roughly Jupiter's orbit, a comet remains frozen and inert. But as it moves closer, sunlight warms the surface. The most volatile ices, like carbon monoxide and carbon dioxide, begin to sublimate, transforming directly from solid to gas without passing through a liquid phase. This sublimation creates pressure beneath the surface, and when that pressure becomes strong enough, gas bursts through the surface, carrying dust particles along with it. These jets of gas and dust create the coma, the glowing atmosphere that surrounds the nucleus and makes the comet visible from Earth. The coma can grow to enormous sizes, sometimes exceeding the diameter of Jupiter, even though the nucleus producing it might be only a few kilometers across. The gas molecules in the coma, particularly water vapor, are broken apart by solar ultraviolet radiation, creating a complex chemistry. Hydroxyl radicals, hydrogen atoms, oxygen atoms, and other fragments fluoresce in sunlight, emitting light at specific wavelengths that give the coma its greenish or bluish tint. The dust released from the comet creates a dust tail, pushed away from the Sun by radiation pressure, the physical push that photons exert when they strike and reflect off particles. This dust tail typically appears yellowish-white because it's sunlight reflecting off dust particles. The tail can extend for millions of miles, creating the spectacular displays visible from Earth. A separate ion tail, composed of ionized gas molecules, is pushed by the solar wind rather than radiation pressure. The ion tail glows with its own light as the ionized molecules fluoresce, often appearing blue due to emissions from ionized carbon monoxide. This ion tail points directly away from the Sun, shaped by the magnetic fields carried in the solar wind. The nucleus itself undergoes changes as the comet repeatedly approaches the Sun. Each passage evaporates a layer of ice from the surface, typically removing a few meters of material per orbit for comets that pass close to the Sun. As the ice sublimates, some dust particles escape with the gas, but others fall back to the surface, gradually building up a layer of dust and larger rock fragments. Over many orbits, this can create a crust of non-volatile material covering the underlying ice, insulating it from solar heating. Some old comets develop such thick crusts that they become inactive, no longer producing visible comas or tails, even when they approach the Sun. NASA's Deep Impact mission in 2005 deliberately crashed a copper impactor into Comet Tempel 1 to excavate beneath the surface and observe the fresh material. The impact created a crater and ejected plumes of material that spectroscopic analysis revealed to be rich in water ice mixed with organic compounds and fine dust. The material beneath the surface appeared similar to, but slightly richer in ice than the surface material, confirming that the interior retains more pristine composition while the surface becomes processed by solar heating. The ratio of different isotopes in comet materials provides clues about where and when they formed. Deuterium, a heavy isotope of hydrogen with an extra neutron, exists in different ratios to normal hydrogen depending on the temperature at which water formed. Measurements of the deuterium to hydrogen ratio in various comets have shown considerable variation, suggesting that comets formed in different regions of the early solar system or at different times. Some comets have deuterium ratios similar to Earth's oceans, while others differ substantially, helping scientists understand whether comets could have delivered Earth's water. The dust particles in comets are themselves diverse and complex. Some grains are crystalline, showing that they formed at high temperatures, possibly near the young sun, then were transported outward and incorporated into comets forming in the cold outer solar system. Other grains are amorphous, formed at low temperatures in the outer reaches. This mixture indicates that the solar nebula was not a static, orderly system, but rather a dynamic environment with extensive mixing, where materials formed in the hot inner regions could be transported outward and vice versa. Comets also contain tiny pre-solar grains, particles that formed around other stars before the Sun existed and survived incorporation into our solar system. These grains have isotopic compositions distinctly different from solar system materials, marking them as true interstellar visitors preserved within comets. They're typically only nanometers to micrometers in size, but they're extraordinarily valuable because they provide samples of stars that lived and died before our solar system formed, preserved in these frozen time capsules. When comets break apart, as they sometimes do when tidal forces or internal pressure cause the nucleus to fragment, the exposed interior shows the layered structure built up over billions of years. Some regions are richer in ice, others in dust. Some layers contain different mixtures of volatile compounds. These variations likely reflect changes in conditions in the solar nebula as the comet grew by accumulation, recording the changing composition of material in the comet-forming region over time. The darkening of comet surfaces producing the surprisingly low reflectivity observed by Rosetta and other missions results from the organic compounds being altered by solar radiation and cosmic rays. This radiation processing, called space weathering, gradually darkens and reddens the surface materials over time. The very dark surfaces of comet nuclei tell us they've been exposed to space for long periods, accumulating radiation damage that has transformed the original icy material into a darker, more complex mixture. Comets are messengers from the outer solar system, preserving materials that have remained largely unchanged for over 4 billion years. While planets have been geologically active, melting and reforming their materials countless times, and asteroids have been heated and altered, comets have remained frozen in the deep cold of the outer solar system, maintaining their original composition. They're samples of the primordial solar nebula, the disk of gas and dust from which the planets formed, carrying within their icy matrices the water, organic molecules, and mineral grains that were present at the dawn of the planetary system, offering glimpses into the raw materials from which everything in our solar system, including Earth and ultimately life itself, was constructed.